Okay, I'm going to make a little short video on capacitors. Maybe you'll get a little better understanding of it. But what I'm showing here, a forum member asked me about clamp-on DC meters, and he didn't believe they made them. Well, since I have this case open to get my FET meter, I decided to just go ahead and show them for the grins and giggles. This one here is for an alternator. You notice how you just hold it across the wire. The next one, if you look at it, it's for a starter. Notice I can read all the way up to 600 amps DC with it. So yes, they do make them. The AC and DC amp meters are actually basically the same. They work off of the magnetic field strength principle, but on the AC meter, the meter is calibrated to read the AC component or equivalent of the DC current. Okay, in this little clip I'm going to show you a few various different capacitors. Capacitors can be marked by color code, by numeric numbers that give you the actual readings, or by codes, and also by letters giving percentage of tolerance. But I found an interesting little thing. It's called a resistor capacitor color code calculator. If you run across any of the old color coded capacitors, which was very common in the old CRT televisions, you hardly ever see them anymore. And on the back side of that, it doubles as an inductor color code. Some of these are the titanium, some are the poly. The one all the way over to the right is an old electrolytic. Those are not so hot. That one actually came out of an antique radio. Thank goodness they got away from them old paper and foil capacitors. Then you have the ceramics. The little orange one right there was a very popular replacement for the capacitors and submagnetos. Of course, this one's rated too high, but they used to call them orange drops, and if you get them in the right microfarad and voltage rating, they work wonderful in the magnetos, because a lot of those old capacitors like that are actually used in high frequency applications. Okay, I'm going to pick me a capacitor out of my plunder box. A lot of these I salvage from old television stuff. Every now and then I run across a need for them. I'm going to use this Sprague capacitor. Sprague is a very well-known capacitor. They're made extremely well. They hold up. And if you notice, it's a microfarad of 40. It's got a working voltage of 110 volt DC. And notice the plus sign. A lot of electrolytics are polarized, which means you have a positive side and a negative side. And when you apply these in the circuit, you need to make sure they go the way they should. Okay, the first meter I'm going to use is my Radio Shack FET meter, or field effect transistor meter. It's an analog. The FETs are way more sensitive, especially if you're going to be doing radio or television work, than the regular VOM. But there's something interesting I will show you. Notice in the back of this meter, there's two batteries, a 9 volt and a 1.5 volt. The way the ohm meter works, the original designs were basically a two-coil balance system, where current would flow through two coils, and you really didn't have to zero the meter because it was more or less self-balancing. But in these type of meters, the current that is used for the ohms is actually, in this meter, the 1.5 volt C cell. Now, the way they usually test a capacitor using an analog meter, it's only really good for a go, no-go test. It really isn't that much useful information because the capacitor could still be kaput. On this particular meter, since it uses a series resistance to measure the ohms through a galvanometer meter movement, this particular meter, you have to zero the leads in order to make sure you have an accurate reading. But really, for the capacitor, it's really not needed. Okay, on this meter, usually they'll tell you to use the highest setting because when you use the highest setting, if you do have leakage, it will show up toward the end of the scale. I'm going to dispense with the leads, so I'm going to put this capacitor directly into the ports on this meter, and we're going to give it a go. Okay, I have inserted the capacitor into the hole. I'm going to turn it on and use the highest scale. Alright, notice what happens. The meter will deflect, and as it charges, it will go back over to the other side. The reason being it does that, when you first turn it on, the capacitor is discharged, the needle will swing all the way to the right. But apparently this capacitor had some charge in it. And it's not unusual for a capacitor to take a charge just sitting in the atmosphere. But either way, you can see this thing is charging. If it goes all the way back over to the zero, then it's usually considered good. But remember this, you're only testing at 1.5 volts. Now I'm going to time lapse this to make the video short, and as soon as the meter stabilizes, I'll show you the reading. Okay, it's been a while. If you notice, the capacitor did not fully charge. Well, this would be indicative of a slight amount of leakage. Is this leakage going to affect the circuit? Good question. But leakage is one of the #1 problems with capacitors, especially in the ignition systems. When they leak, sometimes they'll run it rough, sometimes it won't start at all, sometimes they'll do good. But I'm going to remove this and I'm going to reverse the leads. Okay, now I have reversed the leads on this capacitor. Once again, I turn it on. Notice the capacitor is charged, so it swung all the way. Now, as this capacitor starts discharging and recharging in the other way, the needle will again once swing over. Once again, I'm going to time lapse this. Okay, now you see it had discharged itself. Now it's starting to charge again. Now, normally what you would do, you would let it charge all the way back to where it was. And it should stop where the other test stopped at. But I'm not going to go to that point because this meter here, even though it's a FET meter, is sensitive. It's still, at best, a go, no-go. I'm now going to use a fluke digital meter. I'm not going to put it on the megohm scale because it'll take an eternity for this thing to charge up. So I'm going to use the 20K scale. And I'm going to hook it up proper polarity first. Okay, I'm going to put the other lead on. Alright. Now you see, this is going to recharge. Since I didn't discharge it all the way from the last meter, it's going to charge up. And if this capacitor is good, it should go until it's infinity. Because if there's no current flowing through it, it should have a zero resistance. But we can see that this capacitor is sort of struggling. So that kind of tells me there's something possibly wrong with it. The other meter did allude to it, but the digital also is showing that possibly something wrong with it. So we're going to test something else. Okay, now I have hooked this up to a capacitance meter. Once again, you got to zero the leads out to remove any capacitance. Now this capacitor was 40 microfarads. I have it on the 200 ohm UF scale. Notice it's reading 51.6. Now, if this was a 20%, if I add 20% back to the 40, this thing should be running 48. So this thing's a little bit out of range. Now, this capacitor has been sitting in that box a long time. It might just be needed to be reformed. And yes, you can reform them. But I want to give it a better test. A test that actually dynamically tests this thing at rated voltage. Okay, I want to use my handy dandy Syncor Z meter. I want to test this thing dynamically at the rated voltage. This thing here can test all the way up to 1,000 volts. And when you see that little red light blinking, you better be careful. Okay, the rating on this capacitor was 110 working volts DC. So I'm going to hook it up to the meter. Okay, she's hooked up. So I'm going to come over here. I'm going to set my scale at 100 volt because I do not want to over voltage this thing. So I'm going to test it as close as I can. The first thing I want to do is check for value. So I'm going to push the value button. Well, my other meter was fairly doggone good. This thing is testing out at 52.5. So now I'm going to test leakage. So I'm going to press the leakage button. Now the 8s that you see right there are over range. And it's not unusual for that to happen when you take a capacitor. Now if it keeps into that range, I can block this thing and reform that capacitor. But it looks like this one here is pretty good. Let's see if she'll go down to 0. Okay, that's telling me something right there. You see how it's floating around? So this has a leakage problem or issue. So I want to see what is the allowable. Well, look like it might be reforming itself. But anyway, this thing is struggling. So I want to check the chart and see if this thing is still usable. Okay. If you remember, this thing was 40 microfarads. So I'm going to go down to 40 and I'm going to go across to 110. Closest I can get is BA47. Let's see here. $291. Okay, that came out to allow maximum allowable leakage according to this chart. It would be 291 microamps. But because it's struggling, I most probably would not use this. It wouldn't be worth the cost to even solder it in when I can find one that has zero leakage. And one other thing that I want to test on here also is the equivalent to ECR. So let me get this back out of the red range. The ESR is the equivalent series resistance of a capacitor. So let's see what this sucker's got. Okay. This thing has enough resistance in that sucker to produce about 1.5 ohms, which is really not that bad. So other than the capacitor being a little bit high on the rating as far as capacitance, I want to assume that's a 20%. It's a little high. The ESR looks good, and the leakage is in acceptable range. The only issue I have is the value floats around. So, like I say, if you're going to go to the trouble, why put in an iffy part? Just as soon find you the one that you need. Oh, by the way, that was a leakage, not the value that was floating around.